Hey guys, welcome to episode 1 of the mathematics series. If you're interested in the series overview, I'll link that up here in the card. But other than that, let's get right into it. So this is episode 1, logic and proofs, and we'll be talking about propositions, predicates, and then we'll go into connectives, quantifiers, and then we'll jump over for a little bit, we'll talk about axiomatic systems and proofs, and that will be the video. So let's start out with propositions. So in the eyes of mathematics, a proposition has exactly one bit of information, okay? A proposition can either be true or false. So it could take one of two values. One of those values is called true, and one of the values is called false. Okay? And so that's how mathematics sees it. How we interpret it is as a statement that is either factual or negative, either positive or negative. It is either telling the truth or it is not. Okay, so that's propositions. And these include things like x equals 5 is a proposition, 1 plus 1 equals 2 is a proposition. These are examples of equations, but there's other propositions like it is raining, right? Those are all propositions, okay? Or and these could all be true. Let's do one that we know is false. So like 2 is less than 0. You know, that's a false statement, but it's still a proposition. Okay, so propositions. Next thing is predicates. So predicates are very important to math. Pretty much everything in math turns out to be a predicate, which we'll see. And it's something that returns. It's something that returns a proposition. So returns a true or false value. True or false. Okay. So, yeah, you could either say it returns a true or false value or it returns a proposition. Either way. And we'll just start off with an example. So, start off with an example. Let's do P of X is true if X is greater than 5, okay? This is our example. So that defines the predicate P. Now I'm going to write down two different propositions. P of 10 is a proposition, and P of 4 is a proposition. This first one is true because 10 is greater than 5, and the second one is false. So in this example, P of 10 is true, P of 4 is false. Each one of those has one bit of information. And together, these each are propositions. Perfect. Okay. And now the thing about this is, what if we were to say something like P of blue? Right? P of blue. Now we could say, okay, well, the statement blue is greater than 5 is just completely false. It's not correct. So we could say P of blue is false. But instead of doing that, what if we do this? What if we say we don't want to talk about colors? We want to talk about a specific class of things, okay? So in this series, a class, we'll talk about it next episode, is basically just class, short for classification of things. It's you could think about it as a collection of things, but it's really a classification of things that we want to talk about. So I'm going to write this. I'm going to write P colon R. And what this means is for this predicate P, all I want to talk about is the real numbers. I just want to talk about numbers, okay? And this notation that I have here will show up when we talk about functions. But P colon U means that we're restricting our attention to a certain class of things, this class U. In this case, the class is the real numbers, but this U is the universe of discourse. This is what we call it, universe of discourse of P. Okay. So there's a little bit of notation there, and then once we get into functions, we'll see how this works, how we have a map from some space to some other space, and we'll look at how functionality works and how this is a special type of relation that we got the Cartesian product there. So it's a predicate on a Cartesian product, and we'll talk all about that. One other note that I'm going to make is the class of propositions. So we'll define a classification of things called propositions. These are things that have true or false values. One bit of information, you could say. And the class is prop. This is going to be the class of propositions that I'll label here. And then we'll do a similar thing for the class of predicates. It'll be pred, my bad. Class of predicates, okay? So perfect. With that information, we have all we need to talk about connectives and quantifiers, which are our next two sections. So let's start off with connectives. So 1.3 connectives. Okay. So a connective, this is how I'm going to define it. A connective is a predicate of propositions. Okay. So I'm going to write prop. So remember, prop is the class of propositions, and a connective C is a predicate that restricts its attention to the class of propositions, and I'm going to write a little n here because to denote that it could have n inputs. So before we had a predicate of one input, we could have a predicate of many inputs, x, y, z, for example. And here, this would be a predicate of degree 3, and then this connective here that I have restricted is a connective of degree n. Degree n connective. Okay. So I want to look at let's start with degree 1. So n equals 1. Okay. There are 4 connectives of degree 1. The easiest one is the identity connective, and then we have the negation connective. Then we have the top and bottom connectives. Okay, and they're defined like this. So they all act on one proposition, and in any case, they are true. We're going to define them when they are true. I'll start up with these first two, okay, and then I'll come down to these ones. So the first one is true if P is true. This is the definition. Okay. The second one is true if P is false. Okay. So the first one is the identity, right? So it just returns whatever value you input. It doesn't change anything. The second one is the negation, so it's the opposite. It flips whatever value you give it. If the input is true, then the output is false. If the input is false, the output is true. So it flips whatever input you give it. So we call this one informally, we'll call it the not connective. And then down here, the thing about these ones is it actually doesn't depend on P. It doesn't depend on what P is. This one is always true, and this one is always false. So these are the 4 possibilities, the 4 possible ways you can change a single proposition, one value. These are ways that you could operate on one bit of information. Okay, there's 4 different ways. So these are our unary connectives, unary operators. Now let's look at n equals 2. Okay, so binary connectives. Okay, so n equals 2, binary connectives. We have, let's start off with the conjunction. So the conjunction of P and Q is true if P is true and Q is true. Okay, so the conjunction is the AND quantifier informally. And then we got the disjunction of P and Q. Very similar. This is true if P is true or Q is true. Okay. So this is the OR quantifier. And then we got one last one that we'll really look at, which is the implication of P and Q. This is true if P is false or, I'm not going to write or in quotations, or Q is true. Okay, and so we can easily see a correspondence between the implication and the disjunction. This is equivalent to the disjunction of the negation of P and then Q, like that. Okay, these are equivalent. Now, as you can see, once we start combining these connectives, the notation starts to get a little bit how to say it, like sloppy. It starts to get a little bit stuffy, junky. So let's fix this by eliminating these parentheses and commas, and let's start writing them as just for these connectives and just for these connectives, let's, instead of writing negation of P, let's instead write negation of P without the parentheses. Same thing, right? It's just we're eliminating some of that writing, not as much writing mileage, pencil mileage going on there. And instead of writing some connective, binary connective, especially for binary connectives, let's write it as P and then the connective in the middle, okay? And then this actually works really well with our language because we say P or Q. We say it in that order. We don't say or of PQ, So this is going to work in a lot of different ways, intuitively and notationally. So if that's the case, then we could instead write this as not P or Q. Okay. And then this is understood to be parentheses here. It's just kind of implied when you have that negation on there. Some more conventions for you. Perfect. So that would be connectives. Now let's go to quantifiers. .4 quantifiers. So a quantifier, Q, is also a predicate. And the last example, connectives, were predicates restricted to propositions. These are predicates restricted to predicates. And again, N. Of any degree. So let's start off with the universal quantifier. Okay. The universal quantifier. Okay. And let's also talk about the predicate that we had before. P of x is true if x is greater than 5. Okay. So x is greater than 5. That statement is not true for all x. So intuitively, what the universal quantifier is saying that for all x, p of x is true. And so automatically we know this is false, okay? And then notationally, instead of writing it like this, similar to how we wrote connectives in a slightly different way, we're going to notationally write this as for all x, p of x. Because again, it works really well with our modern day language and intuition. And again, this will be called the all quantifier. Next, we'll look at the existential quantifier. So existential. The existential quantifier is this backwards e here. And in this case, it is true because the existential quantifier is saying that there exists some p. So we read it like this. There exists some x such that p of x is true. Okay. So again, these quantifiers, they're taking a predicate as their input and they're giving you a result. They're giving you a proposition, a true or false value. And these are, I should note, these x's, these are variables, right? These are bound variables. So similar to how in other areas of math you have bound variables, like when you're writing sums and you go say like n equals 1 to infinity or something like that, that n actually has nothing to do with the structure itself. It's just kind of a placeholder that we use to write out formulas a little bit nicer. Similar thing here. Makes it a little bit nicer to write out. Works with our intuition really well. And this will be called over here the exists. Okay. Now what about other quantifiers? Well, we don't really see the symbols for other quantifiers, but when we have longer statements, like for example, for all x, there exists a y such that p of x comma y is true. Okay. So a statement like this is one quantifier here, okay? Because this is quantifying some variables, and then it's taking this predicate as its input, and then the whole thing is a proposition. But this first quantifier is not the universal or the existential quantifier. It's a new quantifier. Let's call it Q. Okay. Okay, and it's defined in this way. So Q of P is a proposition, okay, that's defined this way, and that defines the quantifier Q. So you can input any predicate into here. You could say Q of R, and it would be the same thing. You just replace P with R, and you get a different proposition. So that would be how quantifiers work. So we talked about propositions, predicates, connectives, and quantifiers. Now let's talk about proofs. Okay. So proofs, I think I had green for these ones. Proofs start off with axiomatic systems. Okay. So an axiomatic system is some choice of propositions, okay? So you choose a sequence of propositions. Let's call it A1, A2, A3. And it's a finite sequence of propositions. And each of these little propositions are called axioms, okay? And these are things that we use to prove other propositions, okay? These axioms are supposed to be not tautologies, not contradictions, and they're not supposed to be provable by your previous structure or previous understanding. They're supposed to comply with your understanding, and they're supposed to show you new information. So basically, you start with these axioms, and what an axiom, what a proof is is you're saying assuming the axiomatic system is true, assuming all these propositions are true, then these are your results. Then you prove some proposition. So if this axiomatic system is valid, then this result is valid as well. That's what a proof is. So 1.6 proofs. Okay. So a proof of a proposition P within an axiomatic system A. Let's say A is this sequence. Another thing you could do is you could put a conjunction in between each of these, and then you just have one axiom, okay? And you could call it something like an axiomatic congregate. And that way you only have one axiom, and you say an axiomatic congregate is a choice of proposition. And then you could say an axiom is a factor of that axiomatic congregate when you factor A into when you factor A by conjunction. Okay. So proof of P within axiomatic system A, or axiomatic congregate A, is a sequence S1, S2, S3, ... up to some, it's a finite sequence, I'll call it M, is the last step. And I should note here, these are called steps, such that, well, one of the things that we want is that, actually, such that, well, we want the last step to be the proposition that we're proving. Okay, so we want to arrive at the proposition that we're proving, P. Okay. The other thing is, or the last thing is that for all steps, so I'll go for all I within this range from 1 to M, for all steps, let's see, either S sub I is a tautology. Okay, so the tautologies are things that are true just by their logical nature. Okay, they're not conditional statements. They're not conditional on anything. They are simply just logically true. So one example would be, it is raining outside, or it is not raining outside. Currently, it is raining outside, so that statement would be true. Anything that says P or not P, this is an example of a tautology. Because if P is true, then we know, okay, well, this whole statement is true because that was one of the options. If P is false, that's also an option. So this statement is always going to be true. So we could always use steps of that form. Another thing that we could do, so I'll write or, actually, I'll use some of our notation here. Or S, well, I'll say there exists a J, and where is that J? It's in the range 1 to N, and remember N was the length of the axiomatic system. So there exists an axiom such that S sub I is that axiom. Okay. So far we want the last step of the proof to be the proposition we're proving. And we also want each step to be true in the sense that it's either a tautology or it's an axiom. Or there's this third case. Or there exists a J and a K in between in the range, right? And then in this case, it's going to be strictly less than I. So there exists two steps before the step that we're talking about, S sub I, such that those steps together imply S sub I, imply this step, okay? So this is where all the power comes from in proofs, because yeah, you could import tautologies into your proof as steps, you can import axioms, but you're not going to get any new insights until you use this third thing here, which is implication, which is yielding something new. You take two things, you put them together, and then you get a new result. And that's what this is all about. So that would be a proof, is you start at, necessarily, you either started a tautology or an axiom, and then you add another tautology or an axiom, and then you could do the same thing, or you can combine the last two steps to get something new. So you keep on doing that, you chug along, and then eventually you hopefully arrive at your proposition P. Or you could arrive at not P, and then that would be a proof of not P, or a contradiction of P. So there you go. That's proofs. That was the first episode, Logic and Proofs. I think it went really well. If you guys want to learn more, next episode is going to be episode 2, Sets and Classes. That's coming out on next Monday, Math Monday. Stay tuned for that, and I'll catch you guys in the next one.